Okay, so now that we know a little bit about the Cartesian product of two sets. So we talked about the Cartesian product of two sets, for example A and B. We said that basically if A and B are two sets, for example A is A, B and C, and if B is, for example, C, D, E and F, or D and E, for example, the Cartesian product of A and B, which is denoted by A times B, A and B being two sets here, is going to be a set containing all the ordered sets, is going to be a set all the ordered sets A comma B, such that A belongs to A and B belongs to B. That is basically the Cartesian product of two sets. And what that means is that basically then, for example, in this particular case, then A times B would be equal to basically this set A comma D, A comma D, A comma E, and then you have B comma D, B comma D, B comma D, excuse me. You have B comma D and B comma E, and then B comma E, and C comma D, and C comma E. So that's basically the Cartesian product of two sets. Now as an example there is a concept called basically the relation, and in order to understand what relation is, we need to basically have an example over here. So suppose that we have two sets, for example P, having basically P being this set over here. P is, for example, A, B and C, and Q is the set of basically 5 names: Ali, Banu, Binoy, Chandra and Divya. Now you see that this set has basically 3 elements and this set has 5 elements, meaning that n of P is equal to 3 and n of Q is equal to 5. So the Cartesian product of P and Q, has 15 ordered pairs, which can be listed as P times Q is equal to, for example, A comma Ali, A comma Banu, A comma Binoy, A comma, for example, Chandra, and so on and so forth, and you can go all the way up to C comma Divya, for example. So there you will get basically 15 15 pairs. So now you need to pay attention to this example, so that you understand what a relation is, and then based on that you will understand what a function is. Now what we can do here, of course you see you have all of these 15 pairs over here. Now what we can do, now we can obtain a subset of P times Q, by introducing a relation R, a relation R between the first element X, between the first element X and the second element Y of each ordered pair X comma Y as the following, as R would be equal to basically all the ordered pairs X comma Y, such that X is the first letter of the name Y. X is the first letter of the name Y, and X belongs to P, and Y belongs to Q, So then basically once you get these 15 ordered pairs over here, now you can obtain a subset of the elements of P times Q by introducing a relation R between the first element X and the second element Y of each ordered pair X comma Y as this. And this could be any rule that you could basically define, meaning that you take the first element as X, you take the second element as Y, for example, and then you say that, for example, X is supposed to be the first element, the first letter of the name Y. And then we say that X belongs, for example, to P and Y belongs to Q, meaning that these first elements are supposed to come from the set P, and these second elements are supposed to come from Q, and that's basically how you can get a subset of this set. And so if I go through all of the elements that I would get here, what I would get would be basically R would be basically this set over here. So A would go with only Ali. Because A is the first letter of this name, and it cannot be the first letter of any of these names. Now B can go with Banu and Binoy. B can go with Banu and Binoy. C can go with Chandra. And of course with Divya, none of these letters will go with Divya, so we will get only 4 basic elements in the subset R. which is just a relation which is a subset of P times Q. Now a visual representation of this relation R, called an arrow diagram, is like this. So let's say that you have the set, for example, the set P, which has basically these elements A, element B, and element C, and then you have all of these names over here. You have Ali, you have Bahanu, you have Binoy, you have Chandra, and you have Divya. And so the relation would, a visual representation of this relation would be Ali, A to Ali, B to Bahanu, and B to Binoy, and C to Chandra. So that's basically what the subset basically represents, right? Or can be represented as using this visual representation. And that is basically what a relation is. Okay, so now we have a couple of definitions. So these definitions are important, of course. So definition number, I can call it number 2. So definition number 2. So a relation R from a non-empty set A to a non-empty set B, a relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian, of the Cartesian product of A and B, or A times B. The subset is derived by describing a relationship. The subset is derived by describing a relationship between the first element and the second element, the first and second elements of the ordered pairs in A times B, or the Cartesian product of A and B. The second element is called the image of the first element. So we are already getting very close to the idea of a function. The second element is called the image of the first element. So that's basically one definition here, and that's basically what you must understand it, because that's basically what we did over here. And we have another definition. Definition number 3 is the set of all first elements of the ordered pairs. The set of all first elements of the ordered pairs in a relation R from a set A to a set B, from a set A to a set B is called the domain of the relation R. Is called the domain of a relation R. So the domain of a relation R is the set of all first elements of the ordered pairs in a relation R from a set A to a set B. That's the domain of the domain of a relation R. Now, as another definition number 4. Definition number 4. The set of all second elements in a relation R. The set of all second elements in a relation R from a set A to a set B, from a set A to a set B. So the set of all second elements in a relation R from a set A to a set B is called the range of the relation R. It's called the range of a relation R. The whole set B is called the codomain. The whole set is called the codomain. The codomain of the relation R. Of the relation R. And of course note that range is a subset of the codomain. Now what that means is that, so basically these definitions, from the definition number 2, we said that the relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product of A times B. So suppose that, for example, you have two sets over here, for example, set A having these elements, for example, you have A, for example, you have B, you have C, you have D, you have E, and you have these elements over here. Now, I have, let's say that this is basically set A. I have another set over here, for example, let's say you have F, you have G, you have H, and you have, for example, I. You have this set over here, let's call it B, for example. Now, the Cartesian product of these two sets A times B would be basically all of these ordered pairs, like, for example, A comma F, A comma F, A comma G, A comma G, A comma H, A comma I, A, and then B comma F, for example, B comma F, B comma G, B comma H, and B comma I, and then again you have C comma F, and so on and so forth. You have D comma F, and so on and so forth. You have E comma F, and so on and so forth. So then you would have basically something like this going on in here. Then for example you have B as well over here, B to all of these sets in the set B. You have C, then you have for example D again, all connected to these, and then you have also basically these over here. Okay, so now what happens is that, so this is basically A times B, or the Cartesian product of A and B, and as you can see, you'll get 1 2 3 4 times 5 is equal to 20 ordered pairs here, which is basically 4 times 5 is equal to 20 ordered pairs. You have 5 times 4, so 20 ordered pairs over here. Now basically a relation R, I suppose that you have this is the Cartesian product of A and B. Now what happens is that a relation R is a subset of these ordered pairs, meaning that the subset could be all of the ordered pairs, or it could be basically just a bunch of them, or just a couple of them based on some rule. Suppose that for example I rewrite the sets over here, A, for example, B and C and D and E. These are the elements of A. And then you have F, you have G, you have H, and you have I. And you have these elements over here, B. And then suppose that based on some rule, what I define here is that basically the subset is going to be something like this. For example, let's say that the subset is something like this. Two of them is not, basically two of these elements are not connected to anything, and one of these elements is not connected to anything. And of course, as you can see, this is a subset of basically all of these ordered pairs over here. And we said that this subset is derived by describing a relationship between the first element and the second element of the two sets, or the second element of the ordered pairs in A times B, basically. Now the second element is called the image of the first element. So for example, you can call F the image of A, you can call G the image of B, you can call H the image of C, but you cannot call I, for example, the image of anything, because there is no relationship between any of these elements over here and I in the second set. So I is not the image of anything in this whole scenario over here. Now Now, the definition number 3 that we had was that the set of all first elements of the ordered pairs, the set of all first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of the relation F. So what that means is that, for example, suppose that you have this situation over here. Now, if this was also connected to some element over here, and this was also connected to some element over here, then all of these elements would be the domain of this, and this is some relation, let's call it R, the relation R. Okay. Now, since these two elements are not connected to anything, they are not a part of the domain of this relation, because the definition is saying that the set of all first elements of the ordered pairs in a relation R from a set A to a set B is called the domain of the relation R. And as you can see, D and E are not a part of the ordered pairs over here. The ordered pairs are basically these three ordered pairs, and that's basically it. So these two elements are not a part of the domain. So the domain you can call the domain as A, B, C. That is the domain of R, relation R. Now, the definition number 4, we said that the set of all second elements in the relation R from a set A to a set B is called the range of the relation R. So the range of the relation R. So what that means is that, again, the set of all second elements in a relation R from a set A to a set B is called the range of the relation R. So now what that means is that I can say the range of R is equal to F, G, and H. That is the range of R, basically. And I is not a part of that because I is not the image of any of these elements over here. Now, as a part of basically definition number 4, we said that the whole set B is called the codomain of the relation R. So the codomain of the relation R, therefore, is going to be equal to F, G, H, and I, and that's the whole set B, basically, which is the set B itself. And as you can see, the codomain over here, the codomain is the range is actually as you can see, is a subset of the codomain. Is a subset of the codomain. Here you have F, G, and H. Here you have F, G, H, and I. Now, as a remark, we have a relation may be represented algebraically either by the raster method or by set builder method. An arrow diagram is a visual representation of a relation. So this is an arrow diagram. This is an arrow diagram. This is called an arrow diagram. Now there are two other ways to represent a relation. There are two other ways to represent a relation. And the two other ways are, so basically there are in total there are three ways. There is the arrow diagram. Which is basically what you see over here. There is the raster method, there is the raster method. The raster method is basically I'll tell you about the raster method, and there is the set builder method. Set builder method. So the arrow diagram is basically what you see over here. Now the raster method is basically would be something like this. So in the raster method you would write this relation as in the raster method you would write this relation as R is equal to, for example, A comma F and B comma G and C comma H and C comma H. That is called the raster method. Now the set builder method is basically something like this. For example, you would write this as, for example, R is equal to the set of all ordered pairs, for example, X and Y, such that, for example, such and such relationship exists between X and Y, and for example, X belongs to A, for example, and Y belongs to B, and that is basically the whole story. So that would be the set builder method. So that's basically the three different ways to represent a relation. It could either be basically an arrow diagram, a raster method, and the set builder method. So that's basically the whole story. Now let's go over a couple of these examples. These are important because then if you don't understand these, you will not understand the next part. That's why they are important. Okay, so as an example, so this is a good example over here. For example, I did say a lot of examples in that sentence. So example number 7 on this page is, let A be equal to, let's say that A is equal to, for example, this set over here. Let me change this color. No. Okay. So let A be equal to basically this set, which is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And you want to define a relation R from A to A by R is equal to the ordered sets X comma Y, such that Y is equal to X plus 1. And you want to depict this relation using an arrow diagram and write down the domain, codomain, and the range of R. This is a important and good example. So in order to basically find that relation from A to A, so you know that the relation R from A to A, basically a relation R from A to A is a subset of the set A times A, or the Cartesian product of A by A, where where basically where in all of the okay, so let me break this sentence down, because that way you might misunderstand me. So you can say that the relation R from A to A is a subset of the set A times A, or the Cartesian product of A by A. Once you get that Cartesian product, in that subset so in that subset, the rule y is equal to x plus 1 exists between all pairs of x and y, all pairs of x and y. So what that means is that you need to basically first of all you need to find A times A. So A times A would be basically this set of all of these ordered pairs. For example, 1, 1, and then 1, 2, and then 1, 3, and then 1, 4, and so on and so forth, all the way up to 6, 6. So you would get basically 36 ordered pairs. You would get 36 ordered pairs in that set. Now, what basically and in these ordered pairs, the first element is going to be your x, the second element is going to be your y, and your y is supposed to be, now what you need to do, you need to find a subset of this set, call it R, and in this subset you need to take only those ordered pairs in which basically y is equal to x plus 1, meaning that this second element is equal to the first element plus 1. So for example, you can see that over here, for example, this element over here, this ordered pair is, for example, one candidate. So you can write 1, 2. Then it's not going to happen 1, 5 all the way 1 to 6, and then you can start with the 2. So when you start with the 2, so you have basically your A is basically 1, 2, 3, 4, 5, and 6. So we said that when you start with the 1, you have 1, 1, 1, 2, 1, 3, all the way up to 1, 6. Now what I'm actually looking for is all of those ordered pairs in which y is equal to x plus 1. So for example, this would be one candidate. Then now suppose that you go all the way up to the end of 1, all the way up to 1, 6, and then you have 2, 1, 2, 2, 2, 3, and so on and so forth, in which case basically only 2, 3 would be a good candidate for us. 2, 3, and then you go from 2, 1 all the way up to 2, 6. So only 2, 3 would be on this list. Only 2, 3 would be a good candidate. Then you you start with 3, 1, 3, 2 all the way up to 3, 6. On this list, you have to go 3, 2, 3, 3, 3, 4. So then you have 3, 4 is going to be a good candidate for us. So then you can find, for example, 4, 5 in the next round, and then you have 5, 6, and then you don't have 6, 7, so that's the end of the elements that you get in R. So then you can say that this set R is a subset of the set A times A. Of this set A times A. R is a subset of this set. And the rule the rule based on which we basically got this subset was that we said that y was supposed to be equal to x plus 1. That was the rule. Based on this rule, we basically took these elements out of all of these 36 elements. Now, what you need to do here is you want to depict this relation using an arrow diagram. So if you want to depict this relation using arrow diagram, you have basically 1, 2, 3, 4, 5, and 6, and then you have 1, 2, 3, 4, 5, and 6, and then suppose that this is, for example, set A, and this is also set A, and then you have all of these 1, 2, you have 2, 3, you have 3, 4, you have 4, 5, you have 5, 6, and these are basically, all of these elements have been called y, and all of these elements have been called x. And you can see that in each case, in each ordered pair, y is equal to x plus 1. So 1 plus 1 is 2, 2 plus 1 is equal to 3, 3 plus 1, 4, 4 plus 1, 5, 5 plus 1, 6. And now, so this is the arrow diagram. This is the arrow diagram. Now write down the domain and codomain and the range of R. And this relation is called R. Now the domain of R is basically this set over here, the set of all of these elements that's basically in the first set that are connected to the second elements in the second set. So it's 1, 2, 3 through 5. 1, 2, 3, 4, and 5. The range of R is equal to basically all of these elements that are the images of all of these elements over here. So it's 2, 3, 4, 5, and 6. And the codomain of R is basically all of the elements of the second set, which is 1, 2, 3, 4, 5, and 6, which is the same thing as set A. So the domain is 1, 2, 3, 4, 5. The range is 2, 3, 4, 5, 6. And the codomain is 1, 2, 3, 4, 5, 6. So that's basically how you solve, for example, this problem, and you need to understand every bit of every basically step that we took over here to basically solve the problem. It's important, and it's the very basically the very bone and marrow of functions, basically. So you need to understand it very, very well. Okay, so that is that. Okay, so now we have another example over here. there is a figure over here which is something like this. So if you have basically 9, 4, and 25, 9, 4, and 25, and these are basically mapped to 5, 3, 2, 1, 5, 3, 2, 1, and then -2, -3, and -5. And then you have basically this, the relation 9 to 3, 9 to -3, 4 to 2, and 4 to -2, and 25 to 5, and 25 to -5. So you have this, this. Let me do this properly so that you can see the colors. And I will use this color over here so that you know what's going on. So there is this relation over here. This set has been called P. This set is set Q, and that's basically your that basically shows the relation between the set P and the set Q. Now you want to write this relation in set builder form. Write this relation in one set builder form. Set builder form, and number 2 in raster form. And also you want to identify the domain and range. And of the relation. So in raster form, basically it's usually easier to first write your relation in raster form to see what's going on, and then you can write the same thing in set builder form. Meaning that you can write this as, for example, in raster form you can write this as in raster form you can write this as, in raster form you would write this as 9, 3, 9, -3, then you have 4, 2, and 4, -2, and then you have 25, 5, and 25, -5. That you can call R as a relation. And then you can see that now in set builder form, you can write is R is equal to basically all ordered pairs x, y, such that basically your y is the square root of or you can say that x is the square of y. X is the square of y, and basically x belongs to P and y belongs to Q. That is in set builder form. This part you can write as basically x is equal to basically y is equal to, for example, the square root of x. Meaning that, for example, over here, if you take this as Oh, I'm sorry, the mosquitoes. Okay, so then if you take this as y and if you take this as x, then you can say that basically y is equal to the square root of x. Of course, this is not the principal square root, just the square root function, meaning that the square root of 9, meaning that in this definition the square root of 9, for example, would be plus or minus 3, something like that. Now to get rid of the confusion, you can just simply write it as x is the square of y, basically. So that way you can write it. Now the domain of R is basically the set of all the elements that have been mapped to some element in the range of your function, which is 9, 4, and 25. The range of R is basically all of the elements that some element has been mapped to. For example, 5, 32, 5, 32, negative 2, negative 3, and negative 5. Negative 2, negative 3, and negative 5. So that is your range. And you can see that, for example, this element 1 over here is not related to your range, is not related to your domain, but it would be related to your codomain, meaning that you could say the codomain of R is equal to this set 1, 2, 3, 5, 1, 2, 3, 5, and negative 2, negative 3, and negative 5. So 1 would be related to your codomain, but not to your range, because nothing has been mapped to it. And of course, this is basically the set Q. This is the set Q, which is your codomain. Now, there is an important note here that says that the total number of relations that can be defined from a set A to a set B is the number of possible subsets of A times B. So the total number of relations, I don't know why mosquitoes today. The total number of relations that can be defined, defined from a set A to a set B, from a set A to a set B, is the number of possible subsets of, possible subsets of A times B, which is basically the Cartesian product of A and B, as you know. So if n of A is equal to P, and n of B is equal to Q, then n of A times B is equal to P times Q. We already know that. And the total number of relations and the total number of relations would be 2 raised to the power p times q. 2 raised to the power p times q. Now I don't really know how they have calculated this. So p times q is basically the total number of the elements in A times B. Meaning that, suppose that, for example, you have a set, for example, you have 2 elements over here. Basically you have basically these 2 elements over here, and you have some set B which has, for example, you have these 3 elements over here. Now the n of basically A times B would be n of A times n of B, which is equal to 3 times 2, which is equal to 6. That means that the number of the elements in A times B, meaning that if you write A times B as a set, then you would have one element, another element, another element, another element, another element, and another element here. 6 elements over here. Now the total number of, now having this A times B over here having 6 elements, then the total number of relations of this that you could define based on this A times B would be 2 raised to the power 6. 2 raised to the power basically p times q. 2 raised to the power 6, which is whatever that is, doesn't really matter, but that's how you calculate. And this 2 raised to the power 6 is basically the total number of subsets of this set. Okay, so then you need to just simply, for now, just keep this or memorize this if you need to, and then we will use it in different ways. But what that means is that basically, for example, the subsets of this set would be, now first of all, let me see what is 2 raised to the power 6 is 64. So there are 64 possible subsets of this set having basically 6 elements. So you have so you could, for example, take this first element, and then you could take the second element and the third element, and so on and so forth. You would get six different subsets, and then the first element with the second one, and so on, and then you could have many different combinations, and that comes to 64 different or distinct subsets. And that is basically, that is the same thing as the total number of relations that can be defined considering A and B, and of course the Cartesian product of A and B. So that's basically this which is of course something important you need to, well, of course, like I said, I don't understand how they have calculated this. It's not been given here or proved here or anything, but, well, it's definitely important and useful in many different sorts of situations. And I suppose, I don't know, let's not think about that. Now, Let's do this example here and then we will end this video. So as an example, we have let A is equal to the set having these two elements 1 and 2. Let B be equal to 3, 4, and find the number of relations from A to B. The number of relations from A to B. Find the number of relations from A to B. From A to B. So we said that now n of A is equal to 2, n of B is equal to 2. So then n of basically A times B is equal to 2 times 2 is equal to 4. So then the total number of relations from A to B would be 2 raised to the power 4, which is equal to 16. So a relation R from A to A is also stated as a relation on A. This is also important as a remark. A relation R from A to A is also stated as a relation on A. This is the kind of language that they use in this kind of situation. Okay. Now there is a couple of examples here. We will go through the examples in the next video and then we will get into functions. So I'll see you in the next video and thank you.